We are starting a new track today, the interoperability track. And our lead-off speaker today is going to be Todd Schneider, followed by Will Sobel. And so we should have we have an impressive pair of speakers on our panel today, and looking forward to a lot of new ideas. So Todd, go ahead.
Yes, sir. How do you do, everybody? As Ken just pointed out, we're starting a new group of sessions on focusing on interoperability and, of course, how it relates to, or dependent upon, or facilitated by ontologies. So I'm going to give just a few slides here because I want Will to have most of the time. He has a very interesting perspective and a huge amount of experience and knowledge that he's going to share some of it with us today. So I'm going to talk about interoperability from the perspective of scope. Now, scope is an acronym in the bottom, and it's at the bottom of the screen here. Systems, capabilities, operations, processes, and enterprises. It was I'll call it a document. It's a model for interoperability assessment that was created by an organization that is now defunct. However, myself, Hans Polzer, and Terry Longstreth have the copyright to that, and we've been working on version 2 of it. Version 1 is available at the website. You see the URL down there. I have to say it's very poorly written. The organizations at the time did not want to spend the money for a good technical editor. However, some of the ideas that are there are understandable, if not well presented. So let's press on here so we can get to Will's talk. So, of course, what is interoperability and what are some definitions? Well, I have been looking at some of the ontolog forum dialogue about definitions, and I'll say a little more about that. But from the New Oxford American Dictionary, it's the ability of computer systems or software systems to exchange and make use of information. And of course, then there's the issue of groups of people. How can they operate effectively together? However, from the scope perspective, that is the scope model for interoperability, we think of interoperability as the ability to communicate effectively. Now, I realize that's somewhat ambiguous, and we try and clarify that a bit with a rather simple model of communication. So, in terms of communication, there are these paths that we have to consider that seem to be the most relevant. People to people, people to machines, machines to machines, people to machines to people, and of course now machines to people directly. And in terms of communications, well, they use all sorts of natural languages, image, sounds, symbols, physical gestures, haptic mechanisms, and there'll probably be new things in the future that I can't think of right now. But what about the semantics of interoperability? You know, my perspective is a Tarskian perspective. It's the particular way in which something is understood or is explained. But the important point from interoperability, as we are explaining it in terms of the ability to communicate effectively, is misinterpretation. So I may want to convey some notions, some ideas, or some actions to a receiver, or receivers, plural, and I may not take into appropriate thought the context of the receiver. However, in terms of the notion of interpretation, I expect or I hope that the receiver will interpret something sufficiently close to what I had in mind. But be in mind that notion of misinterpretation is something that's done by the receiver of a communication. I thought I spelled out everything clearly, but obviously I did not take into account some information, context, or knowledge the receiver or receivers may or may not have. So semantic interoperability from the scope perspective is this ability to use the information that's communicated by a sender so that the receiver's interpretation of the information is sufficiently similar to the intended interpretation of the sender for the purposes of blah, blah, blah. So there's a lot of words there. And again, it's still somewhat ambiguous, or depending on your perspective, very ambiguous. However, interoperability depends on language. And of course, ontologies use languages. Natural language terms and definitions, which we'll say more about, are usually ambiguous. But as humans, they're critical for our communication between ourselves and between other things that we create. So, in many cases, natural languages are used for ontological constructs. Of course, you can use strings of alphanumeric characters, but at some point, you have to present a user of an ontology with some explanation as to how they should interpret that symbol. And of course, well-constructed ontologies, as Nicola has pointed out many times, are there to constrain the interpretations of those symbols, specifically the non-logical symbols of the intended models. But interoperability also has a scope. How much do you need? It has a cost, both financial and organizational, process costs. You have to change your processes. So what's the scope? How much do you need? How far does it go? What does it encompass? Or what should it not encompass? What have you failed to think about? Which is usually a problem when you get to interoperability. So again, with ontologies, what's the scope of the ontology? Have you explained the context in which you expect it to be used? That is, it entails a context, and if the receiver does not with or infer errors. As Barry pointed out, we should never build an ontology unless we have some recognizable use for it. That is, we need to know the scope. So that's all I have to say. And let me turn this over to Will. And now Will's talk is entitled The Evolution of an Industrial Standard from Paper to Ontology. So Will has been working with complex systems, architecting them across various industries for a long time, like 30 years or more. For the past 19 years, Will has been the chief architect and chair of the executive committee of the MTConnect Standard. And if you're not familiar with MTConnect, it's an international model-based standard for manufacturing equipment and the IIoT. He also, and very fortunate for the Industrial Ontologies Foundry, leads the architecture working group and is responsible for actually getting stuff out the door for us. He expends a great deal of energy in that regard. So thank you, Will. He's also, while leading the architecture of the MTConnect standard, he was CEO of Vimana.
Vermont.
You'll have to correct me. Thank you, Will. It was an industrial analytics platform. And before that, he worked as a visiting lecturer at UC Berkeley, teaching web development, data center optimization using machine learning. And before Berkeley, this gets real interesting, Will worked in the financial industry for 17 years. He's also served as a vice president and chief architect of NCSI Mara. So, Will, let me stop sharing and let you have the floor.
Thanks, Todd. Let me just start the share. And there we go. Yeah, so luckily Todd just said everything there is so I don't need to do an introduction at all. But thanks a lot, Todd and Ontolog Forum for inviting me to speak here and prattle on about what I've been doing over at MTConnect for close to 19 years of my life and what we are hoping to do and planning to do to address some of these issues that Todd brought up. It was a very interesting discussion on scope. So what I want to talk about today is information models and information model standards in particular, and what they do and often what they don't do, and how we've gone from being just a paper-based standard all the way to being to approaching the ontological definitions that we're going to be getting into. So the purpose of information models, and this is like how MTConnect started, a lot of the other information modeling standards that started, was there for communicating data from one system to another. And they provide just enough semantics to get the data tagged properly and structured properly so it can be interpreted on either end. And they do this to try to be efficient about it. So they try to, make efficient use of bandwidth. The document formats are often easy to interpret, but they have issues. They don't make adequate commitments they are underspecified. There's ambiguity in the way they do the definitions and the terms, and I'll get into that a little bit more as we go along. And what we end up doing is creating things like XML schemas, JSON schemas to be able to validate that they're structured correctly and that the data is formatted correctly. But this doesn't get us everywhere we want to go. The other issue that we get into is when we actually imbibe these standards into the destination systems, the model is not there. The model is only used for reference. And this means that we don't get a lot of the model richness when we start to interpret that data. What we do is we just get the information without any of the abstractions or anything else. So this is a bit of an issue. So standards and interoperability, since this is the interoperability discussion. And, in statistics, all models are wrong, but some are useful. I'd say in information models, they're all underspecified, but again, some are useful. We have undercommitment in standards that leads to the ambiguity in interoperability issues. Ambiguity, I think, is one of the key problems that we have when we're defining these models and we're defining terms and creating definitions. And we need to use ontologies to be able to provide the semantic layer that really helps us to derive the meaning and get over some of these ambiguity terms. And as Todd was saying, when we produce the information, we need to be unambiguous about that. And when we imbibe the information and bring it in, we need to be unambiguous about that as well. So we're going to explore this from two different dimensions. We're going to look at it from a validation perspective. And this is partially in my role, trying to bridge some of these domains of sort of information modeling to ontology. This is one way to be able to sell this idea to some of the people in the information modeling and standards community. That one of the things everybody complains about is our ability to validate the models. And one of the use cases that I found very compelling for why we need ontologies is in the exploration of the capabilities of manufacturing systems all the way up to design. Now, just to be sort of clear about this, I'm going to be talking about this from a very domain-specific perspective. I'm looking at this from the manufacturing systems perspective because MTConnect is a standard to communicate information from a machine tool, from a machine tool's perspective and viewpoint to manufacturing systems. So we're going to look at it a bit from that perspective, but this is I think a good way to talk about how we've proceeded down this journey. So from the validation perspective. So what we look at from validation, a lot of what we're focusing on in information model standards is validating the data that is being represented by whichever documents or representations of the standards that are being created by these systems. We very rarely actually talk about validating the model itself. Does the model make sense? So I'm going to talk about this a bit and how we've proceeded from being a PDF XML schema standard through to a model-based standard in SysML and machine readable to using things like OCL to start to validate some of the constraints. And now we're going into Shackle plus OWL to look at validating more of the shapes, going beyond just a simple SysML model, and also doing hygiene tests, and then getting into the OWL and axioms. So we started early days, and this is about 19 years ago, in 2007, like almost all other standards in this space, using a PDF specification that was generated from a Word document, translating that PDF specification manually into an XML schema, repeating a lot of the information that was in that document, like all the definitions and everything else, inaccurately, of course, into that XML schema. And giving us probably within the XML schema, we could probably do like maybe 20, maybe even generous, 15, 20% of the validation by applying the schema to the documents that were generated and saying, okay, are they formatted correctly in XML? In other words, the containment hierarchy. are the cardinality, the things that are supposed to be there are there. Does the controlled vocabulary match up? And are IDs unique? And the references to those IDs, do they actually resolve to something? Not necessarily the correct thing, but to something. That we could basically do with what we had. Of course, all of our requirements themselves were written in text. There was no real structure to those. We could only do tree structured validation. When we have also multiple documents, we had problems with that. And there wasn't really a taxonomy. I remember even early days of MTConnect trying to explain the idea of generalization or specialization to some of the community and running into a real roadblock, not even having the tools to be able to currently even diagram it or show how you could have layers of abstraction. So, and of course, no commitment. So what happened was with this approach, we hit a wall. We couldn't really even model types and type relationships to each other very well, given the tools that we had. We couldn't create relationships between documents. MTConnect is made up of, let's say, well, generally three parts. There's sort of the meta model, which describes the machine, the components of the machine, the relationships of those components to each other, and the various different pieces of data you can get from those components. And then another document which describes the data itself that's streaming. So the observations that are made about the data that you can collect from those components. And a third one, which describes what we call assets, which are things like, the cutting tools, cutting tool geometries, the where, the so forth. Things like, parts, processes, files, other things that you use within the manufacturing process as a third set. But we relate all those together with various different IDs across documents. And can't really document those at all because there's no facility in a PDF to do so. And it made it really difficult, except for just saying, hey, this refers to that. Interesting property types, subsumption of property types, not really a possibility either. And we were, again, the model itself is defined sort of between XSD and PDF. We put the XSD diagrams in the PDF, and nothing really contained the same model. And we had problems because we were like cut and pasting continuous between those. One of the things that a lot of standards that are like XSD based is they're kind of limited by what they can express, but what you can express in XSD. So if you're using XSD as your modeling language, it's not really a modeling language. You can only do a limited set of things. And what you end up doing is you're limiting your model by what you can express in XSD. And for that reason, we went to SysML as model normative. That was around 2015 or so. The transition did a couple of things. First off, it meant that our model was now machine readable in XML. And we could start to actually create a normative definition of things like generalization relationships between various different things like blocks. And we could start defining our data types with units. We could start having a better control over things like cardinality, specialization. We could start getting into behavioral models like state models and activities and use cases, requirements, all those kind of things. So in general, a lot better than what we were dealing with before. Everything was in the model. So we could generate, because it was machine readable, we could generate the XSD and the schemas and everything else out of the model, which meant we didn't have the copy and paste problem that we had before, where we'd have dissimilarities between what was in the XSD and what was in the model. And that was a big mess. But there's still things that we couldn't really do. There were like, mereology, the relationship between things, how they were connected and such, the parts, the unity requirements. Transitivity wasn't really possible. One problem with SysML is that you can't really you can't really express very well the instance data. So when you can create like examples as instance models, but they it's very hard to do that on a regular basis, like importing that into the SysML model and then validating within the tools. Like you can do it within Cameo, but it's very tool specific. It's not very easy. As well, we can't really handle any of the meta properties that we want to be able to handle. So there's still additional levels of what I'll call validation that are required beyond what we could do with SysML. So what we ended up doing is we started adding, to be able to handle some of the sort of deeper level validations, we ended up putting like OCL constraints to be able to say what was required, like multiple level down, cross property constraints, all those kind of things. We put it in as OCL, but OCL has issues. It's complex syntax to use. You're vendor locked with whoever has implemented the OCL. In this case, it was just with Cameo. And there weren't that too many tools, especially open source tools that we could use to be able to validate the model. Again, we were still focused on the instances, the instance data. Not we haven't even got into validating the model itself. So we hit a wall with SysML. We couldn't validate the actual model against some of the conformance requirements that we have. And this is things like if you talk about, naming conventions for the various different classes and properties and relationships, how those are supposed to be formatted, what we call each side of them, what we call the relationships themselves, and consistency when we use relationships across multiple different parts of the model. All of these things we can't really do in SysML. Of course, there's a lot of things we can't really express in SysML either. We can't express any adherence to a theory. We can't express things like disjointedness or equivalence between classes or sufficient conditions for that matter, or complex shapes. So if you wanted to express like what is the correct expression of a certain part of the model as a graph, not really way to do that in SysML. I mean, you can grant the blocks and their relationships, but how do you validate that? And then also the concept of property subsumption. I can't create something like a subproperty that is related to other properties. So I'm trying to express things like, let's say, mereology, and I want different parts relationships. I really can't express that level of specificity. And again, there really aren't particulars, as I said before. This is a problem that, if I want to, let's say, have a dozen different implementations of this model and I want to get that data into the model and validate it, it's not an easy process to go through. So there's no easy way to import the information from the information models, from the expression of these documents, back into the SysML model and then run the validation on it. That's not an easy process, and it makes it really limits what you can do. Again, we can have a machine readable model, we can export it. And we actually have done this, and there's a product out there for MTConnect, which is a validator that True Analytics has produced that does exactly that, extracts the SysML model and creates a validation suite that then gives you a validation report. But there's nothing automated about that in the model itself, and that is a real lacking. And again, we can't validate the model. Does the model make sense? Does it adhere to a theory? Do we have any logical issues built into the model itself? And if you look at like you take it, let's say, an auto-clean approach, and you're looking at things like identity, unity, rigidity, there's no easy way to validate that we haven't violated certain rules within the model itself. And that means that, and I think this is true for almost all the information models out there, there are validations galore. And I know that MTConnect has a lot of violations just in areas like the way we deal with some of our process occurrence as a component. Components are supposed to be like most physical parts of the machine. we've kind of jammed something in there. Why? Because it's convenient to be able to communicate information that way. But there's identity and unity issues right there. These are problems that, because as an information modeler, you do things for convenience of communication, you don't often think about, am I am I communicating that meaning as well correctly, not just the information, the data. That's definitely a concern that we need to deal with. So we started this process of moving to an ontology, and we're doing it in multiple phases. The first phase is just let's get better about validating the model itself and adherence to certain conformance and constraints and consistency rules. And then let's make sure that we can also validate the implementations of this model through some of the metadata, as well as our various different reference document types like JSON and XML, convert those into a graph, and at least apply a basic shackle-based analysis of that data to make sure that the shapes that are being corrected are correct and follow not just the hard schema requirements of the standard, but also some of the ideas that a device should have a controller has paths within the axes component. You can only have linear and rotary deprecations, various different structures, relationships between various different parts of the machine, how they're related both topologically and mereologically. We can express all that and get much better at least validating that this implementation of the standard is correct, and that the standard itself follows certain rules and find problems in the standard, and make sure that as we add new things to the standard, we again don't violate any of those rules. So if we look at the validation process, there's the ontological, basically the model validation, style and rule constraints, conformance consistency, as well as the instance models in particular validation that we are creating a representation for a particular, in this case, a machine or a device that follows the requirements of the standard, that the meaning imbued in the standard as we understand it is being communicated correctly. Not entirely, and again, probably, as much as we can do with just the shapes, but as a first step. Second step is we're going to be moving towards a full OWL ontology of the standard, and this is going to be done in collaboration with IOF. So IOF is working on some of the bits and pieces that we need, like in the system engineering group. And, PPS has other pieces, maintenance has other pieces of it. So what we're going to do is start to take what we're doing sort of as this initial flavor of the ontology, which is not going to be great. And we're going to start moving that into a ontology that has a strong ontological theory underlying it, with BFO as a TLO and IOF as a mid-level. And then refactor the various different parts of the standard so that we have a better defined set of definitions, and the definitions will be grounded with axioms that, again, will tie us to a higher level theory and meaning, so that the standard will be better grounded. And we're going to build those right into the SysML model. This is something that maybe will make my brain hurt, but basically we want to, again, be model normative and keep the various different axioms around what we're doing inside the model, and then we'll be able to project that out into OWL. Hopefully this will work. We'll probably have to build some scaffolding around it to make it all kind of hang together. But the general idea is there will be the information model, and there will be the ontology. The two will tie together. They'll join. We're not going to replace the information model. The information model is still, as I said before, it is useful. It communicates the information from the machine to the applications. We just want to make sure that what it's communicating from the machine to the applications is more consistent, is validatable, and now also adheres to a higher level ontological framework. So to do that, we are going to create a set of parallel ontologies, make sure that it validates through the reasoner, add additional things like disjointness, equivalence, restrictions, sufficient conditions to the model that we have. And then we can start also creating things like rules based on the entailed graph, asserted and inferred facts using luckily open source tools that are available to us, like PyShackle and such, to do the validation. So this gets us from where we were, which is basically schema validation, all the way to now entailed validation. So the pipeline for this validation is going to look like something like this, where we take the SysML model, we do the XL export of it, we take the instance diagrams, we export those, we bring those into a graph, we run the reasoner on it, get the entailed graph, we run shackle validation on it, we get the validation results out the other end. We also get any issues that occurred during the reasoning. And now we've got, and the hope will be, we have now a validated model, meaning the model is correct, the implementation of the model is correct, that it doesn't violate any logical constraints within the ontology. And since we've tied the ontology to a principled upper level ontology, IOF and BFO, that we have now also validated larger domain agnostic way. We are not just sort of correct within our domain. A lot of what you see also when I've seen ontologies projected out to, information models projected out to ontologies, is it just kind of like, okay, we're going to convert our XSD schema to an ontology and call it a day, and they get a mess. That approach I don't think is gonna work, or at least not for very long, because again you're just replicating your ambiguities to the ontology and you haven't solved any problems. So we have to really focus on resolving those ambiguities. I'll talk a little bit more about that in a second. The validation today, basically, when we talk about where we are now, I think, we started out with like XSD, maybe 20%. We got up to like 45% with the SysML model. I think with OCL and other things, we can do about probably 60% of the model. Again, we're just focusing on particulars on the instance documents. I think with the Shackle Owl, I put it at 95%. I don't know. I'd say 100% because that's always being a bit ambitious. But I think we can get pretty close to being able to validate the model if we apply both hygiene level shackle validation. We also validate the model and logical consistency against a principled higher level, mid-level and upper level ontology. And we follow and we create adequate axiomatization of our own terms and first order logic definitions, that we actually have something that we can then say this is correct from both the model, and then the implementations, if they follow that, will then be much better defined, as well as much easier to use within this destination systems. So bring it back to interoperability, and if we're thinking about, again, higher level domains, interoperability across multiple different domains, what we're talking about is really, I have a bunch of different standards. Let's call, for example, let's say A and B, and I want to map them to some system. Let's call that M. That's a combined union of those various different standards. And let's say that A has identity issues. And that means that basically we have to invent what those identity criteria are for that particular standard. And then let's like make life even worse, because this is usually the case. We have that same standard, but implemented from two different providers. And then we have to actually interpret, because A is not clear, it's ambiguous about exactly what the identity criteria are for various different entities within that standard. We have to create two different interpretations, one for S and one for T. Then we have, let's say, another standard, B, and that has, let's say, non-equivalent representation. So there's multiple different ways you can represent the same proposition, so that we have to pick one when we implement the integrated standard M. So again, we have two different ways that they chose to do it. Our S and T implementers both did things differently for that standard. Now, what happens is we end up creating from these two underspecified standards and what effectively becomes a third standard, or ontology M, that neither of the two initial standards actually endorse. So what we end up creating is our own sort of undocumented fork of those two standards that have to make these assumptions about identity and equivalence, and also then an interpretation, which is a guess from these two different sources, that may or may not be correct. And because it's ambiguous, we end up creating this union that is not just sort of an additive level, in my estimation, of ambiguity, but we have sort of this multiplying effect of ambiguity, because we have an X by Y problem where now we're trying to guess across 7 different things in this third ontology that has ambiguity all over it. And we merge this information if nothing is well defined. That gets us to a point where really it's a mess. And to sort of elucidate some of this, I'm going to talk a little bit about capabilities. This is a driver that I've used for the necessity of ontologies in the manufacturing domain. So this is to support things like agile manufacturing, and it's actually necessitated if you're going to look at things like the digital thread. So to talk a little bit about agile manufacturing, basically we have a set of product requirements that are coming down. They specify things like, the functions, general geometries of where things need to fit, the operational conditions, and so forth of a particular product, or a part of a product that forms into assemblies and eventually gets turned into a thing. There are many different ways of making that thing. You can use like a subtractive, milling, turning, where you move material, additive, where you add material. You can do castings, forgings, what's called near net, a bunch of different ideas about different ways you can engineer the manufacturing of this particular thing. And so that those different ways give you a set of manufacturing requirements: the mass of this thing, the type of materials, the tooling that's going to be required, and a whole bunch of other constraints on those processes. You then want to match that set of requirements with a set of capabilities that are provided by various different pieces of manufacturing equipment. If we look at this across an entire enterprise, we're looking at something that, from the enterprise level, can we make this? Can we satisfy your requirements? And let's say it's a DoD part and a whole bunch, let's say, ITAR, and which is export control, and let's say security requirements. Do we have all those capabilities at the enterprise level? From the shop level, do we have engineers, machines, operators, inspection? Can we make it at that level? So we have capabilities at that level. Then we get down to the machine level. Can we perform, let's say, 5-axis machining, which is required on this part? And then at the part level, we can then infer upward, or we can then assert that, okay, I can do 1,500 Newton meters of force, and I can squirt coolant at 80 bar, etc. And then we can sort of create these emergent set of capabilities up through the various different parts of the organization to be able to say, yes, I can do this. Now, of course, this requires, again, like from an MTConnect perspective, we're down at sort of the machine and the part of the machine space. But what we need to be able to do is communicate that up, and then also work with other standards that can talk about the engineering capability, the inspection capabilities, the operations, material handling, and everything else that go up through the organization, which then has to bring in things like IT capabilities into the mix. And all these standards, all these ways of being able to express these capabilities from the bottoms of those all the way up to the top, I need to somehow be able to talk with the same level or same meaning so that we can then reason over that and say, okay, yes, we can do this. And we need to be able to do this not with a lot of humans in the loop, but we need to be able to do this almost in real time, meaning we need to be able to ask these questions and get almost immediate responses so that we can make decisions if we're going to get into any level of agility across our manufacturing supply chain. And the requirements from, like, let's take a implementation example. So I was going to drop down a little bit and look at, so in MTConnect, what we've done, I sort of did a little example here. It'll show how some of this could actually work axiomatically, is looking at, and don't talk, I want to talk about systems right now. We're working on that in IOF. So if I wants to drill down on that, we can talk more about that in the standards organization. But basically, I mean, think about it, let's say at a high level, a system is something that has a set of capabilities. We can talk about like linear motion systems having prismatic motion capabilities that can assert that. We can talk about things like then the infer capabilities of things like 3-axis motion capability is having 3 linear motion axes and 1 continuous revolute axis. If I want 4-axis motion capability, I can say it's 3 axis plus another indexed revolute motion capability, and then I can aggregate that up to the cell. Now, from what we were just talking about, basically I can take those capabilities and I can move up through that and then start talking about, okay, 5-axis being another revolute motion capability. Then I can assert that. I can assert the various different parts of the machine through these axioms, which I can then build into my standard and start talking about then the capabilities of individual systems all the way up and build these up as composed set of business rules. So I can translate my use cases and my business requirements into axioms I can then apply to my various different manufacturing systems. So the pipeline will then turn into collecting data from the data sources and producing the information models, like I was showing, which with a small commitment. So again, we need to get better at when we produce the information models, when we define the standards, collecting the data from the data source, we need to get better about even committing of definitions that are well-formed and well thought out. We don't have to go the full level of commitment at this point. We can just commit to making sure that things are validated and correct, as we're talking about for invalidation, so that we can then start reasoning over them later. So then we can transmit, again, we're using the information model as a communications device to transmit that information across. We can then take it in from those documents. As long as we've done the commitment on the left-hand side, the right-hand side, the validation should go okay. Import the information model, map it to the ontology, validate that that information is correct, and then assert the full commitment on the knowledge graph and the ontology once everything's in there. The transformation process has to become normative, and the definitions need to become normative. And we need to start getting better at the commitment on the left-hand side when we're producing this data so that we can get better on the commitment side on the right-hand side. Again, we're still going through the same medium, but we're getting better at our definitions. We're getting better at our ability to represent that data in a way that will be ingested, and then we can add additional meaning to it. So where do we go from here? We can't actually replace these information models. That ain't going to work. DINSpec is 50 years old, still being used. Almost every machine tool in the world is currently using what's called G-code, which was optimized for vellum tape. Those are reel-to-reel tape readers. Hasn't changed. We need to figure out how to first evolve standards from paper-based to model-based, so at least we get to a machine-readable form and get them into something that, again, we have as a good communication mechanism to the model or the information model standards development organizations and their community, and acts as an intermediate. Then we need to sell SDOs on why ontologies are necessary. And I used concerns like validation and capabilities as one way to be able to sell that, because there are compelling ways of being able to talk about what we can't do in standards in the information models, and what we can do when we actually start bringing in ontology, that we can actually create these like complex axioms. We can start, reasoning on the axioms. We can do better levels of validation and so forth. And then we need to convince standards organizations to also create principled ontologies. That doesn't mean just like, a pop ontology or a simple ontology that converts a SysML or a XSD model directly to an ontology without adding additional commitments and well-defined theory. We need to make sure that when they do the conversion, they do the mapping, that it actually adheres to ontological principles, ontoclean principles, and they're doing it right. And last piece is they will actually need a lot of help. Well, one of the things that we can use as a driver for this also is, of course, I talked about it up to this point, but it's on everybody's mind now, is AI. One thing about AI, we don't get it right in the standards, in the information models, and in the ontologies. We keep propagating this ambiguity up through the various different models. AI is not going to be able to resolve that ambiguity. If there's ambiguity in the way we represent things and the way we define things, that is just going to propagate itself right into the AI models that we build, and it's going to increase the ambiguity in whatever the hell they derive from it. So if we can't correctly represent our information coming in, then AI is not going to help us. So we need the ontologies to be able to help the AI understand what the information means, what the data means, what the ontologies mean. They have to clarify the ambiguities. They have to clarify all of our violations across identity, unity, rigidity, so that we can correctly understand what this information means, so that we can solve problems like being able to do agile manufacturing and reason across that information to improve our global manufacturing systems and build a cohesive digital thread that actually makes sense and we can cross domain boundaries. So I kind of went quickly here. Probably covered too much information. Hopefully I didn't lose too many people or make any really big ontological faux pas, but that's about all I got.
Well, thank you, Will. Are there questions? I certainly have some. Will,
Yeah.
if I understand this correctly, you're not talking about implementing a knowledge graph for the actual data at this point, are you?
So we're actually talking about doing both the knowledge graph for both the data, I mean the information that's coming in as well as the model itself. So doing the ontology for the model, but also being able to imbibe the uh, the documents so that we can validate both the model and the implementation of the model.
Okay. Well, I have two
Yeah.
more questions at least.
Okay. So
If you're in the validation process, if you come across inconsistencies, how do you go back to the standard and correct that?
yes. So what we do is um, well, so there's pieces of the standard that are going to remain the same. Again, for the process of communication of information, I think they're usually okay. Uh, I see there's some chat on things like step NC, and so forth. But if you even look at the step standards, there's a lot of, if you look at them from sort of an ontological perspective, there's a lot of different ways of doing things, such as the way they represent PMI, the way they represent various different constraints. Uh, there's issues, and what we do is we're going to put into the model a set of axioms right into the SysML model, and then being able to extract those, and again put that framework below it, so that then we can start mapping it down to the um, the ontology. Again, what this, if I understood you correctly, is going to look like is a combination of ontology and information modeling and SysML modeling that will then be able to map the incoming data and the ontology uh, into the same graph. So uh, I'm not sure that answered what you were asking.
Yeah, I think you got
Yeah,
to it,
okay.
but I
Okay.
better let John have his time here. So, John, if you'd like
Yep.
to ask some questions of Will.
Okay, okay, the point that I keep making is that you must have, at a barest minimum, full first order logic. And OWL
Mhm.
is just such a rinky-dink subset. The first thing you must do with OWL is translate it to full first order logic. With that, you can map it to and from conceptual graphs. You can map it to and from any version of logic you wish. And so first order logic is the barest minimum for knowledge representation. And you can go beyond that to common logic and subsets that have a little more expressivity than that. And that's what Tim Berners-Lee was trying to do. And unfortunately,
Mhm.
the accessibility gang got this idea that first order logic was too much, and they have this horrible subset. And OWL is just so rinky-dink. You just cannot represent
Uh,
everything in OWL. It's just a tiny, tiny subset. You must have FOL as the barest minimum.
Yeah, I mean, it's one
well,
reason why within
John,
in yeah, sorry, go ahead.
John, I don't think anyone disputes that. The issue is
Mhm.
whether you can get people to accept it. Getting people to accept OWL, even that, has been a challenge over the last decade or more. Finally,
Yeah,
people are acknowledging, oh, yes, it's much better to use OWL than just use, as Will pointed out, SysML or XSD or whatever. Getting people to the next step is like a couple of quantum levels higher in terms of trying to use first order logic. I'm sorry, Will, you
yeah,
were going to respond?
yeah. And I was gonna say, John. I
No,
mean,
no.
I'd agree with what you're saying. One of my issues is, of course, It's the available tools and technology that are available to work with first order
Right.
logic. And if we're going to sell it, again, I'm looking at this almost from like, how do I convince the industry to get better? That's my problem. My problem is, the industry is still looking at, okay, a PDF document and an XML schema is good enough. And I'm trying to get them to say, okay, how do we get, through model-based even to ontology? And they look at me cross-eyed. So basically what we need, it'd be great, yeah, if we had something better that was implemented in like, graph technologies and we had full first order logic, theorem provers and things like that, but we don't. We're stuck with the tools that we have. So if we can get, I mean, I'll be happy, even though it's, yeah, I agree, rinky dink. Even if we can get the community to adopt, let's say, OWL and DL at a minimum, then I think we'll be a huge step beyond where we are right now. And if we can even get to tooling, I mean, look at a lot of the technology that's out there right now. It doesn't even implement DL. We're talking like most tools out there, if we're lucky, can get us to like RL, right? So then we need to, just if we think about progression of the industry from or the standards environment, and again, trying to do interoperability across multiple different information models and standards, we have such a large distance to cover. I think, let's take this piecewise and let's use the technology and the tools, and at least the available capabilities that we have at this moment, and exploit them as much as possible so that eventually we'll be able to get to what you're talking about.
No, that's the point is that the AI revolution has completely changed everything. All the current tools can remain.
Mhm.
And if you translate this into first order logic, you have a very clean and simple translation to and from ordinary language. And that's where everything is going. So that what happens is that all of those tools are going to be available, but through a normal translation to ordinary language is the uh, to and from, and with first order logic as the representation for the future. So all future tools are going to be based on AI systems in which ordinary language is the primary means of communication. And once you've got that, all these old tools, every single one of them becomes just a legacy that can be mapped to and from the future, which the future is full first order logic and actually beyond. You can have additional extensions beyond first order logic to include a much broader range of logic, and
Well,
with with the mapping to and from ordinary natural language as the medium of
Mhm.
expression. So that's coming, and it's coming very, very rapidly. AI enables that, and what I'm saying is that that entire base of all those tools based on OWL and everything else is dead
Mhm.
end. I'm not saying dead end, but obsolete tools that are going to be mapped to the new future in very, very soon, within the next, it's already happening.
so John, let me interrupt you right here. I understand first order logic, and I know it's the way to go, but we have all of this stuff out there that's in OWL. Now, would you say that you could go from your OWL constructs to first order logic easier than just
Absolutely.
starting out, just starting with
Abs
just natural language standards and text and then going to first order logic? So that is, we have
Absolutely.
a stepping stone, if you like.
The mapping from OWL to first order logic is very simple, and it simplifies things. It's much easier to map FOL to and from English than to map OWL to English. And so the more general you have, and with the tools that we're getting now,
So,
you can just completely, all of the old systems we have to recognize are obsolescent. they will continue to be used indefinitely, but the future direction is first order logic with ordinary natural language as the means of communication.
Yes, I certainly agree with that. But as you probably aware, I'm sure you're very aware that having a large organization convert all of their information systems overnight or even over a couple of years is probably not going to happen. Trying to find a way to ease them into this newer way of doing things is going to be the real challenge. And I know you and your company are working on that or have been.
The old systems never die. Systems that are 50 years old are still in use. So they will
Yeah.
Yes,
continue
I
to be
know.
used
They
indefinitely. But the means of
they can't afford
communication
to
to and
change
from
them.
will be English translated to and from uh, FOL.
Okay, well, we're over time right now. Does anyone have any other questions of Will?
Yeah, I was just actually responding to the auto step comment in there. I did a little bit of an analysis of that. I mean, if you look at like edition 5 of steps, AP 242 edition 5, and they were looking at like the identity issues. They actually went over to an entirely new identity scheme using a new set of EUIDs instead of adopting the identity schemes that were built into STEP. Why? Because there are problems. Again, you see a lot of this in a lot of the standards that are out there that they have identity issues, unity issues, where the way that you compose and talk about various different ideas or parts of the standard are not well defined, or there are multiple different ways of doing this. So we have, equivalency issues, a lot of different problems within these standards, and we need to sort them out. And that's, I think, again, going back to the layering approach, I think what we can do is layer the ontology on top of a lot of these models and create a better way to interpret the model. And maybe it will narrow down the implementation so that we can remove some of the ambiguity, so that if there are multiple ways of doing it, how to interpret those different ways or narrow those ways to a best practice. That's kind of what I hope.
Uh, Janet, you have a question for Will?
Yes. So this is
Okay.
really, really helpful because it grounds the question of ontologies in this progression from metadata and XML. And so you see that you're adding capabilities and issues and properties as you're going along. What want to do with it? I'd suggest to accommodate John and
Mm-hmm.
that you expand your timeline there and show that
Okay.
alpha is a step, and that then so then one can see cleanly how you go from the one end to the other end, and maybe with a stepping stone there. The other thing is about effective communication. I think agency and intelligent agents and the pragmatics have to be brought in. Effective communication means that it ends up with the appropriate action. And that is another way that you bring in, it complicates your picture, but it really is essential that when you get to interoperability, you want to test for operation, actual actions of agents and environments. And then you have a really nice general picture going from simple metadata up through ontologies to guide effective communication for appropriate action for agents. And then you publish that. Okay. That's great. Thank you.
Yeah, that's great. Yeah, no, I agree that we need to take this further, and no disagreement there. I think also I liked the way you framed that, and I'd like to sort of think about the intelligent agent approach, and maybe backing into some of what you were talking about. So yeah, I'd like to hear more about that.
Okay, well, thank you, Will, for a great
Thank you.
presentation. Actually, looking at some of your slides, it now explains to me why you're interested in capability so strongly. But we need to wrap up since we're over time. Next week,
Yeah.
Mike Bennett will be entertaining us as usual. So we look forward to that. So
Okay.
thank you
Thanks a lot,
all.
everybody, for listening to me. And
Oh, you're
thanks.
welcome, Will.